Okay, so if we consider the steady state limit, all the design considered as synthetical synthesis of analytical procedure, that is nothing but whatever the parameters we have available, some constraints under which we have to design a line. So there are some steady state constraint or consideration which are we are going to see right now. So which are those? First one, maximum allowable bus voltage, or we can say across the equipments for which voltage level is given. So in first unit, I think you might be remember that we have seen that is nominal voltage level. It is in kV, and means each equipment is transmission line. It is having nominal voltage level and its maximum operating voltage level in kV. So if we consider these values, let us suppose nominal voltage is 132 kV. The maximum operating voltage in kV is 145. If we consider 220, 245, 275, it is 300. The same way for 345, 362, for 400 kV line, it is 420. For 500, it is 525, and for 750, 765. So you can observe that near about 20 to 25% increase is allowable. That is in max nominal voltage. Okay, this is the first point which we have to consider for steady state design of transmission line. What is second? Current density. If we consider a particular conductor, its cross-sectional area is depends on current density, right? So while selecting the conductor, we have to consider current density as well as the temperature rise at that location, and accordingly we are going to see select the current density so that steady state uh, limit for design of EHV AC line is done or achieved. So next point is building a corona inception gradient, and for which there are some important factors like we have to fix the conductor diameter and number of conductors in the bundle. We can say third point is corona inception gradient. You know that if this is a conductor, the voltage at this conductor is 400 kV. Whenever we are moving away from the conductor, this voltage is going to decrease. Let us say 300, 200. So gradient is nothing but dV by dx, right? So voltage changes with respect to the distance, and to reduce this voltage gradient, that is because of this corona voltage gradient, corona inception gradient, corona loss is measured, and to reduce corona loss, the energy for these factors are important for fixing the conductor diameter and number of conductors in the bundle. You know that by increasing the conductor diameter, corona is decreases, as well as by increasing the number of conductors in the bundle, we can decrease the corona inception gradient. The fourth point, it is nothing but the electrostatic field. See, this electrostatic field, if it is increases beyond the breakdown voltage of air, then corona occurs. So this is also important point to get steady state design or limit. Third is audible noise, and radio interference. See, we are going to see it in details. which are the values at which we will get steady state limit. So audible noise and radio interference. And next, the last point, it is nothing but the compensation requirement for voltage control. So these are the some factors which are required to achieve the steady state limit. So let us see one by one. You know that what is the equation of power handling capacity? How to define the power handling capacity? The power handling capacity, it can be defined as, means, let us discuss about the first point. What is the first point? It is nothing but the maximum allowable burst voltage, and that can be calculated by using power handling capacity. So the first point, you know that power handling capacity. This is just revision of first 5 units, and we are going to see everything in single unit. That is power handling capacity. It is equal to, you know that, 0.5 E square upon Lx. Lx is nothing but the positive sequence reactance. L is nothing but the length in kilometer. E is nothing but the voltage. Similarly, the percentage power loss, it is equal to 50 into R upon X. See, this is nothing but the ratio of resistance to positive sequence reactance. So based on the total power to be transmitted, the number of circuits can be designed, and the design means requirement, it can be varied as per the location. We have calculated the number of circuits, and this number of circuits calculations, it depends on the power which is to be transmitted. Means in first unit we have seen that we have to transfer the 2000 megawatt of power, and the voltage level, that is voltage of transmission line, it is given as a 400 kV for the distance of 400 kilometer. In that way, by using this formula, we have calculated the power handling capacity and number of circuits required. Okay, so this is first point which is required for steady state design. Second is current density. So the current density, it is for transmission, it is always in between point 0.75 ampere per mm square to 1 ampere per mm square. Means for transmission line, this current density is maintained in between 0.75 to 1 ampere per mm square. See what is happening at this lower values for carrying the same amount of current. See, let us suppose current density, one case delta is considered as 0.75, and another case delta is considered as 1. So if we consider for lower values, for carrying same amount of current, the conductor should have larger diameter. Let us suppose current is of having same value, but if we are going for higher current density, for same amount of current, conductor diameter or cross section is lesser. Here it is greater diameter, and this is for same amount of current. Keep in mind. Are you getting or not? So you know that if we are going for a higher diameter, the corona surface voltage gradient, it is going to decrease. Means, but choice of current density, it affects the corona inception gradient, corona surface voltage gradient. Keep in mind. See, जर मी कमी व्हॅल्यू घेत असेल डेल्टाची, what will happen? Conductor diameter required is more. So as the conductor diameter is more, the surface voltage gradient is lesser, and corona effect, it is reduces. So just keep in mind, the choice of current density, it always affects the steady state design or limits of transmission line. The third point we're going to see is nothing but the charge of bundle conductor. So everybody knows how to calculate the charge on bundle conductor. That is Q is equal to, this is Q is equal to 2 pi epsilon 0 M into V. So V is nothing but the voltage of transmission line. So if we define the voltage, V is equal to V at angle of 1 0 degree, 1 at angle of minus 120, and 1 at angle of plus 120 degree. So this is voltage. You know that M, it is nothing but the inverse of Maxwell coefficient matrix, and C, it is equal to 2 pi epsilon 0 into N. Okay, so the charge of bundle conductor governs the electrostatic field in the line vicinity, the surface voltage gradient on conductor, and resulting radio interference, audible noise, and corona loss. So if we calculate the charge on bundle conductor, ultimately we will get the electrostatic field, because you know that to calculate the electrostatic field we require to know the charge. So we will know the surface voltage gradient, then what is radio interference, what is audible noise, and what is corona loss. So to calculate these values, the charge on conductor, it must be known. Now the fourth point, it is nothing but the electrostatic field. See, these are the terms or some factors which should be considered for steady state design of, means we are going to see the which are the values or which are the factors which are affecting steady state design. So electrostatic field, you know that electrostatic field, if you consider this is a tower, this electrostatic field, it is horizontally as well as vertically present. Means let us say suppose this is conductor, and at point A we have to calculate the electrostatic field. So this is conductor of phase A, again another conductor of phase B. So due to A and B, there is an electrostatic field. Let us suppose due to conductor A, this is distance D, the electrostatic field present is EC. And while solving the derivations, we have split it into two components. One is a horizontal and one is a vertical. The same way, the electrostatic field due to B is, it is in this direction. So these are the two components. So this field, it is due to the conductor in the air. Same way, we have to consider this conductor below the ground, and they are having again two components due to these images of this conductor below the ground. And what we did, we have just, you know that the resultant horizontal and resultant vertical component at this point, it is due to these two conductors. So to calculate the electrostatic field, there are, one is a vertical component, we have derived the equation in I think 30 minutes, and second is a horizontal component. So how to calculate that electrostatic field? The vertical component is given by, it is equal to Qi upon 2 pi epsilon 0 in bracket Hi minus y divided by di square plus Hi plus y divided by di dash square. See, in our case, we have considered xi or yi, right? जे आपण जे डेरिवेशन बघितलं तिथं जे नॉमेनक्लेचर आहे ते वेगळं होतं. But just keep in mind, vertical electrostatic field component, it is given by Qi upon 2 pi epsilon 0 into E. See, in our case, it is xi minus y, here it is xi plus y, right? Okay, the same way, how to calculate the horizontal component at a particular point, which is in the air, the vertical component of electrostatic field EH, it is equal to Qi upon 2 pi epsilon 0 x minus xi in bracket 1 upon here it it is we have used xi, here it is hi. So hi is nothing but the xi, so you can write down xi also, right? It is 1 upon di square minus 1 upon di dash square. So this is nothing but the horizontal component of electrostatic field, and xi is nothing but the horizontal distance of coordinate from particular phase I, because x suffix I is there. And how to calculate di? Di is nothing but, yes, x minus xi whole square plus y minus yi whole square. Sorry, here it should be y I, not hi. yi minus y, and here it should be yi plus y. So finally, this di will be, it is equal to what? X minus xi square plus, yes, y minus yi whole square, square root of the answer. Now, the total electrostatic field, see, we have calculated the horizontal and vertical component. Then the total electrostatic field, it will be, see, this is just one component. Likewise, there are a number of components. Means if EV1 consider केलं तर तिथे काय असणार आहे Q1 upon 2 pi epsilon 0 y1 minus y upon d1 square plus y1 plus y upon d1 dash square. So likewise, there are n number of components. So we have to do the summation of this component, and finally the total electrostatic field is equal to E I square. हे लक्षात येतं का तुम्हाला? आपण हे ऑलरेडी सॉल्व केलेले आहेत, राईट? Okay, so let us move towards next factor, that is conductor surface voltage gradient. Why we are seeing these three factors? Because we have to do the design of HVAC transmission line for steady state limit by considering the steady state limit. So these are the factor on which this steady state design is depends. The next is a conductor surface voltage gradient, which is given by Qi upon 2 pi from 0 into 1 upon n into 1 upon r. Okay. Now, next factor is corona inception gradient. And it is given by E is equal to 2140 into m into delta. आपण फॉर्म्युला आपण पाहिलेला आहे 1 plus 0.0301 upon under root delta r, and this is in kV per meter in RMS. Next factor on which steady state design of transmission line depends, it is radio noise level. So what is radio noise level? It should be, if we consider up to 4 bundles or 4 conductor in bundles, so if we consider 4 conductors in bundle, this radio noise, it is equal to 0.035 em plus 1200 r minus 33 log. So just note it down or keep in mind. No need to note down. Just keep in mind. I will share the notes. The next factor, it is nothing but audible noise. And you know how to calculate audible noise. The audible noise is equal to 10 log summation of k is equal to 1 to delta 10 raised to an upon 10. This formula it is already studied. This is nothing but the summation. If there are number of components which are generating the audible noise, so the total audible noise is nothing but the summation of all the components. And then second last, which is equal to coronal loss, it is given by, see there are different formulas. We have just mentioned one. It is in megawatt per kilometer, and this is used for three-phase line. Keep in mind. Okay, the last point uh, which are required to calculate the, we can say, steady state design, voltage control. Voltage control at power frequency, and you know the how to calculate. These are the all the factors which is already studied. Now, I think there is nothing to say more about these all the factors, 10 factors, because it is already covered. Let us move towards next topic, that is limits, which are governed for design of transmission line and width of the line. So which are the limits? The first one is electrostatic field. So if we consider the ground level, the minimum value of electrostatic field, it should be 15 kV per meter. These are the limits. Just keep in mind. Second point, radio interference. So radio interference, that is for 40 dB and above 1 microvolt per meter at 1 megahertz frequency in fair weather condition. See, radio interference, it should be up to 40 dB above 1 microvolt per meter at 1 megahertz frequency. And this is measured at the edge of right of way. You know what is right of way. Third point, audible noise. So what is limit for audible noise? It is equal to 52.5 dB, right? And this is also at the edge of right of way. Okay. Then next is coronal loss. See, for corona, sorry, not corona loss, it is corona inception gradient. So if we consider the maximum voltage gradient, it should be at least 10% on center phase or the phase with maximum voltage gradient. Let me see. This gradient, it should be at least 10%. 10% on center phase. See, this is the margin. These are the some limits for design of transmission line. It is nothing but the electrostatic field. At ground level, it should be 15 kV per meter. Radio interference 40 dB above 1 microvolt per meter at 1 megahertz. Audible noise, it should be 52.5 dB at the edge of right of way, and corona inception gradient, it should be at least 10% on the center face. This is nothing but the margin given.